Thank you very
Extremely
much.
complicated word, inhomogeneities, I made it. So.
Okay, thank you very much, Peter, for the introduction. Good afternoon, everyone. My name is Apostolos Kanatas, and together with my supervisor, Professor Koltsakis, we have prepared today's presentation with title Stretching the Limits of Battery Modeling to Address Multi-Scale Inhomogeneities. Let's first begin with the motivation behind our presentation. First of all, there are two types of inhomogeneities: non-intentional inhomogeneities, like thermal inhomogeneities that may appear due to the tabs design or to defects like an internal short circuit, or due to thermal management via the heat exchangers. And on the other hand, we have the intentional inhomogeneities, where the cell manufacturer may, for example, design a layered electrode or a blended electrode in order to increase cell performance, or design this anode overhang region in order to decrease cell degradation. Now, as regards battery modeling, the P2D model is a powerful tool. However, it is based on the assumption of perfect homogeneity. So we would like here to find what to do to deal with these inhomogeneities. So we have prepared 3 different example cases, and let's first begin with a case related to a layered electrode. But first, let's highlight some points as regards porosity. There are 2 types of electrodes, ones with low porosity and ones with high porosity. Low porosity electrodes for energy applications, because there are more solid particles to store lithium ions, and thus they display increased capacity, and high porosity electrodes for power applications, as there is more space for lithium ions to move freely, and thus they display increased capacity, increased performance at high C rates. And here we have a proof of this concept, where we have done some simulations with GT-Auto line 1D, where we examine the discharge capacity, which is the capacity that the cell can deliver during discharge until it reaches the cutoff voltage. So we examine the discharge capacity for various C rates, and as regards the low C rates, we can see that the low porosity electrode performs better, while for high C rates, the high porosity electrode is the winner. But we want good performance throughout the whole C rate range. So the question here is, can we have the best of both worlds? And an idea to achieve this is to use a graded or double layer cathode. And in our study, we examined the case where there may be layers with different porosity. For example, if we can see here the cathode, you may have the low porosity region near the separator and the high porosity region near the collector, and also the opposite displacement. So here we would like to go beyond experimental and empirical interpretations. And thanks to the help of GT-Auto line 1D, we have considered a positive electrode with 2 layers. And we considered 2 different cases. In the first case, we have the low porosity electrode placed near the separator, while in the second case, we have the high porosity electrode layer near the separator. Here, for comparison reasons, we also present again the results from this previous slide, where we have considered a single layer electrode with low and high porosity. So if we see now the first case with a low-high design, we can clearly see that for low C rates, it performs somewhere between the low and high porosity electrodes. But the bad news are that for high C rates, it displays the bad performance of the low porosity electrode. But if we look now at the high-low design, we would see that as regards the low C rates, it displays the same performance as with a low-high design. But the good news here are that for high C rates, it preserves the good performance of the high porosity electrode. Of course, we have not answered yet why the high-low design is better than the low-high. And in order to do this, we have to check at the lithium ion concentrations in the electrolyte at 3C rate. So in the first case of the low-high design, we can see here the lithium ion concentrations in the electrolyte and throughout the whole electrode pair thickness. Here, in the high porosity region, we can observe that there is no access to the active materials, and this is due to the fact that the low porosity region appears increased diffusion resistance. But now if we check the second case, the fact that we have placed a high porosity electrode near the separator seems that decreases the diffusion resistance, and thus we can see that there is good accessibility to the active materials. This effective capacity now is limited. The effective capacity that we are interested in is, and we saw before as regards discharge, is limited by this accessibility, and so the high-low design is better than the low-high. And then we can go a step further thanks to the help of GT Auto Lion, and we will try to find the optimal thickness of each sublayer as regards the high-low design. So here we have considered 3 different cases where we have changed the relative thickness ratio. So in the first case, we have 3 times the layer with the low porosity is 3 times larger. The second case is the one that we have already seen with equal layer thicknesses. And in the third one, we have the high porosity layer to be 3 times larger. Now, if we look at the results, we can clearly see that for low C rates, the 1-to-3 ratio performs better. So this ratio is better for high energy applications. And on the other hand, if we look at the high C rates, we can see that both the 2-to-2 and the 3-to-1 designs are good. But if we look the entire range, we would say that the 3-to-1 case performs generally worse than the 2-to design. So we will go for the 2-to-2 design as regards high power applications. Of course, we have to be careful with these optimization results here, as they are highly sensitive to the microstructure and thermophysical properties, which means that we need accurate data. Now let's move on to the second example case that we studied, which is related to the anode overhang. What is anode overhang? Anode overhang is the fact that the anode is usually dimensioned higher than the cathode, and this is prominent in also every cell type, like we can see here for a cylindrical cell. This overhang now is claimed that it reduces lithium plating, so we would like to prove it by modeling, and even better, try to optimize the design. There were some earlier 2D modeling attempts on the topic, but they had some shortcomings, which limit us to study the effect that we wanted, which is lithium plating during fast charging. So here we respond with a 4D cell model, in which model the 3 equations of mass and charge balance also are solved in all the 3 dimensions, instead of only taking the thickness dimension into account, which is what the B2D model does. Furthermore, we would like to track the amount of lithium that is plated, so we have enabled the plating model, which is described by a modified Butler-Vormer equation, which means that the reaction is active only when the local plating over potential becomes negative. So it is preferable also to have the capability to predict the local plating over potential in all the 3 dimensions. Now, to begin our investigations, the first thing to do is to have a calibrated basic model, which means that we need accurate information for electrode microstructure and electrode pair geometry, which we obtain thanks to SEM analysis. We need measurement data in order to calibrate our models, which we obtain with cell electrothermal testing. And of course, finally, we follow an iterative optimization process in order to fit simulations with measurements as regards both voltage and temperature. And then to study the impact of overhang on plating, we have extended our model into the 3 dimensions, and we have applied a fast charging 2C at minus 10 degrees Celsius scenario, which are the conditions that plating is expected to happen. What we are more interested in here is that we need the local plating over potential not to become negative, because then the plating reaction occurs. So if we look at this figure, where we have plotted the minimum local over potential as the current throughput progresses, we can see clearly that as the overhang region increases, the plating initiation is delayed. And this initiation has to do with the fact that the current densities of the negative electrodes decrease as the overhang region increases. Now, the fact that the plating initiation is delayed has a significant impact as regards the capacity loss due to plating. We can see here that as the overhang increases, the capacity loss decreases. But from one point and after, further increasing the overhang region becomes less beneficial. And now let's move on to the last case that we studied, where we wanted to study a more complex system, such as that of a battery module with active thermal management. The batteries need to operate in an optimal temperature range in order to avoid aging. And to achieve this, we usually place heat exchangers, but these heat exchangers are likely to create thermal inhomogeneities. So here we would like to assess the magnitude and the impact of temperature uniformity on battery aging. Now, someone may ask, how many dimensions do we need to solve a problem? And the answer is, well, it of course depends on the problem. So here we may use from 0D up to detailed 3D models in order, if we want to study from particles up to battery module or even battery pack. And now, as regards our simulations, we have set up a battery module, and we have applied a fast charging scenario at 35 degrees Celsius, where ACI layer formation is expected to happen. We also present here the 3D graphs of temperature and capacity loss during and at the end of the CC charging phase. So here, in the first case that we studied, we have applied adiabatic boundary conditions. And if we look at the temperature, we can see that there are some thermal gradients which occur due to the heat exchange with inactive casing. Now, because there is a straightforward relationship between temperature and capacity loss, we can also see that here there is increased capacity loss at the middle cells. The next concept that we studied was to apply a floor cooling boundary condition. And as we can see here in the maximum temperature, in this case, it remains below 50 degrees Celsius. And this leads the capacity loss to be less than half compared to the adiabatic case. Of course, there is still increased aging as we move away from the cooling plate. And to overcome this, we have placed some fins near some of the cells. And here, as regards the temperature, we can see that the cells which are in contact with the fins develop lower temperature. However, if we look at the capacity loss, we can see that the cells without fins nearby still experience increased capacity loss. And now, as regards our conclusions, the main conclusion is that there are scalable, multidimensional models which are powerful tools to study the complex phenomena that may arise from intentional and non-intentional non-uniformities. In the first case, we saw that electrode layering can be virtually engineered to achieve the desired energy power density trade-offs by overcoming the inherent ion diffusion limitations. In the second case, we observed that the anode overhang can be studied and optimized accounting for ion diffusion in all directions, rather than taking into account only the single directional diffusion which is used in the conventional modeling. And in our last case, we saw that intracell and cell-to-cell temperature gradients may result in localized failures, which are not possible to predict with simplified modeling approaches. Thank you very much for your attention. and we would be happy to answer any of your questions.
Yeah, thanks a lot for the presentation. Great work done. Full range autoline 1D, 240. So very nice. I also like the last slide here.